The biggest lie in RAG is that semantic search is simple. The reality is that it's easy to build, it's easy to get up and running, but it's really hard to get right. And if you don't have a good setup, it's near impossible to debug. One of the reason it's really hard is actually chunking, and there are a lot of things you can get wrong. And even OpenAI boggled it a little bit, in my opinion, using an 800 token length for the chunks. And this might work for legal, where you have a lot of boilerplate that carries little semantic meaning, but often you have the opposite. You have very information dense content. And imagine fitting an entire Wikipedia page into the size of a tweet. There will be a lot of information that's actually lost. And that's what happens with long chunks. The next is overlap. OpenAI uses a 400 token overlap, or used to. And what this does is actually we try to bring the important context into the chunk, but in reality, we don't really know where the context is coming from. It could be from a few pages prior, not just the 400 tokens before. It could also be from a definition that's not even in the document at all. There is a really interesting solution actually from Anthropic, contextual retrieval, where you basically pre-process all the chunks to see whether there is any missing information, and you basically try to reintroduce it. So today we are back continuing our series on search. We are talking to Brandon Smith, who is a research engineer at Chroma, the vector database. And he actually led one of the largest studies on different chunking techniques. So today we will look at how we can unfuck our RAG systems from badly chosen chunking hyperparameters. Let's do it. So what do you think? What's the motivation for chunking? Why do we actually need it?
That's a good question. To be honest with you, I do genuinely believe chunking is something we do. We do chunking because we have embedding models. And in a better world, we wouldn't actually chunk at all, right? In a better world, we would extract the tokens that matter for a given query and bring them back perfectly. But that's not what happened. It turns out we can make some very powerful embedding models that are very strong, but they obviously, of course, need an input string. You have to give them an input string. Um, and they need context as well, actually. I guess it's like fundamentally you have a query and you have some passages in the text that you want to retrieve for that given query. And of course, the way we know to do this is that we embed the simple way you embed the query, and then you embed a bunch of chunks of the documents, and then you retrieve that chunk for the given query. Ideally, a better system. In theory, you would actually take the query and really read along the entire, like if you gave it to a person, they'd take the query and they'd read along the entire corpus with that query in hand until they see something that matches and they'd go, great, this is good, these two match. But what we've actually said is when we like embed our corpus, we just do it once. It doesn't matter how the query changes, at least in general, in standard rank, you just do it once. And we do that because it's really efficient. We embed the entire corpus, and then every query, they get their own separate embedding. And we just do a little outer product between them whenever. And really, fundamentally, we chunk because it's just efficient and it's quick, right? A better way, and as I said, this is, I believe, how Cobalt works. And I've also did some papers on that, on Anton, is you can actually like it's not like you just chunk the query and chunk the embedding. The process is done together. You hand the query and like a chunk, and the two then make the similarities found together. You can't just have their vectors held in place. But yeah, to summarize the question, why do we chunk? I'd say it's because it's efficient and quick. That's why we chunk right now.
Yeah, basically avoids to re-embedding the entire corpus we have, which can be like millions of documents on
Yeah,
retrieval time.
absolutely, exactly. And yeah, and it adds latency, right? We want it to be quick. If you're using a chatbot in particular, you don't want the user waiting while it re-embeds everything to get something back. So yeah.
Yeah, and we basically trade off the accuracy for the speed of retrieval, but we can basically add it back in by using re-rankers, just basically doing the stuff you said, just after you
Yeah.
retrieve like a candidate set.
Mm.
And what is the main issues with current methods? I think we have seen so many different chunkers, especially in LangChain, like the Markdown
Yeah.
one, HTML splitters. But I think most
Yeah.
people use like the standard one, just based on length.
Yeah, 100%. Exactly. I think the issue with chunking, at least before our paper, was that no one knew. No one knew it was better. There's actually a lot to be said. There's a whole thing that I'm going to make some posts about, which I think is really interesting. No one knew it was better. Maybe this is a bit of a bold claim to make, but I believe OpenAI themselves also didn't know it was better because there's a chunking strategy they used that wasn't very good, and we'll get into that. But yeah, no one knew what chunking method is better because there's no way to compare it. There's no metric. There's not really a metric. Of course, you go like do the standard RAG metrics and test the entire pipeline, but you're not really isolating the chunker, right? You ideally like to isolate the chunker and say, okay, let's just compare the chunkers. And so that was the current issue is that, yes, as you say, there's no way to see which is better. Fundamentally, one could ask, okay, what would we imagine a good chunking strategy would be? And it's, okay, what is it? At the end of the day, there are two things that matter. Really, all that matters is that for a given query, we retrieve exactly the relevant information to that query. That's actually it. For any given query, you want to receive only the tokens that relate to that exact query. That will be the ideal, best entire RAG pipeline. In practice, we don't have that. Extra stuff come along. So you say, okay, fine, extra stuff's going to come along, but we want as little extra stuff as possible to come along. And a chunker that means tons of extra stuff happens is a very bad chunker, right? So you can say the most trivial chunking algorithm will be one that doesn't chunk at all and literally hands the entire corpus over. That's in theory like a possible solution. It's horrible though because you get tons and tons of useless chunks. Of course, then we have what became really popular are just the fixed token splitter and the recursive token splitter. And they seem very sensible at first. I think the fixed token splitter is the most natural next step. Like, okay, let's just split it into fixed lengths, and then we chunk all of these. And yeah, it's okay, but that could break right through a word. It's not ideal. And then I could go into this. Okay, I'll go into this. I'll hop into this, right? Basically, then, okay, now we're on the idea that we want to break the text into pieces, right? We have now decided that we're going to make this system. We will actually embed everything one time, right? Because we mentioned at the start that the ideal system wouldn't actually do that. It would do a bunch of other stuff and it'd be specific on the query. But because to keep latency high, we're just going to embed everything once. And we just want to find, and to be honest, our paper mentions that the focus really is that given that we want to just embed everything once, what is the best chunker? Because people have mentioned, actually, if you re-embed this stuff, you can maybe do something better. That's not really the focus. Given you want to embed everything once, what is the best chunker you could do there? Fundamentally, obviously, we wanted to retrieve only the specific tokens for a given query, but it's a practical world, it's a real world. The embedding model has to have enough context inside that chunk to be able to bring it back to the query, right? For example, one might I don't know, there might be let's say there's an example of there's a passage and it's about some guy, John, and he said, John buys a red Ferrari, full stop. It is the fastest in town, dot. And somebody queried and was like, how fast is John's car? Let's say our chunking method just literally broke it is the fastest in town and made that its own individual chunk. That would actually never get retrieved because it's got nothing to do with a car. It just said it's the fastest in town. You've actually completely lost all information by just breaking that into its own chunk. You just completely made it useless. You've just deleted it. So even though that's exactly the right answer a person can see, we just pull that thing saying it's the fastest in town, the embedding model has no hope of ever retrieving it because we've broken information, we've removed the flow of things. So that's when it comes to breaking things down like that. Fundamentally, I guess my point with that is that you have to keep the context within the chunks. The chunks have to contain context. That's what matters. And yes, with all these different chunking methods, ideally you have something that has context within it. I'm going on a bit of a tangent here, and I feel like I'm covering a bunch of other questions, so feel free to break me. Maybe we should be orienting ourselves before I go off that pipeline.
No, I like it. So was one thought I would love to get your thoughts on as well was my idea of Misi chunks. Like mutually exclusive, but completely exhaustive, which is something I'm try to get to. But in the end, what I landed on is one of the chunkers, which you also basically implemented in the paper, which is more of the semantically oriented chunker, where you try to basically make the chunks as semantically coherent as possible. Can you maybe start with these? What can it do? How does it work?
Yes, 100%. Yes, I thought a lot about that. Yes, because it really comes back from the initial thought experiment. The one the guy had the fast car, it's the fastest in town, whatever, right? You could look at the chunk, it was the fastest in town. If that was just the entire chunk, and then immediately you can say, this is missing context. This is clearly missing context. There's a pronoun here. I don't even know what word it's about, right? You could almost look at the chunk itself and see if it's a bad chunker by being like, this is just incoherent, right? So we can criticize the chunks itself. Ideally, what you want is a join that produces chunks that every chunk is super coherent and is completely self-contained. And that's what we did with the cluster semantic chunker. And mind you, actually, I won't lie. That's one of those chunkers where I don't know if you saw the paper, there's a picture that I think makes that chunker so clear and so obvious. And that's actually how I built the thing in the first place. What I did was I started off with a recursive token chunker. And I just split the document by 50 tokens, which is like very short, right? 50 tokens is like what? Slightly under 50 words. It's like a sentence, maybe 2 sentences. And I did that too. I wanted to split by sentence, but you never know if there's no sentence, blah, 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 whatever weird HTML document I have. Anyway, so you might have, let's say you have a corpus, you run the recursive chunker over this, you have 100 chunks then, right? And they're tiny, 100 tiny chunks. What I then said is, okay, cool. We now have 100 chunks. Let's embed all of these chunks, and so that we have all their embeddings, and let's find the similarity between all pairs of chunks. And again, there's one of those things where if I say it out loud, it's hard to follow along. If anyone can see, there's an image in the paper you can look at, the cluster semantic chunker. You may have seen it, and it's a big matrix, and this staircase pattern down the middle. I mean, it's a symmetric matrix, so you see these blocks down the middle, and all these blocks, they're sat on the diagonal. They're all on the diagonal. And what that matrix is, it's just a matrix of the similarity between any pair, right? So the top left corner is the similarity. Okay, down the diagonal, that's the similarity between like things in itself, right? So like the very top left corner, that's the 0, 0. That's saying what's the similarity between chunk 0 and chunk 0. And then in the next one, 1, 1, the similarity between chunk 1 and chunk 1. Obviously, that's all 1. So you have 1s down the diagonal. Great. Then your off diagonals around it, you're basically asking a question, okay, so what's the similarity between this chunk and its neighbor, or like neighbor? And sure enough, like I literally just ran that code not expecting to see it, well, not sure what I'd see. But when we generate that matrix, you see these blocks forming down the diagonal. And we did this on the wiki articles corpus. And sure enough, you can see actual articles. And you can see they appear as like a massive block. And that's a single article. Fundamentally, it turns out that if you break an article and you get the similarity between all their embeddings, they're all very similar. And they're all very different to different articles. So that's basically the logic that starts the cluster semantic chunker. It's, wow, I can literally see it. I can literally visualize the pairwise similarity between all chunks, and I can see things that are like different contexts and different themes. So like, why don't we try our best to make a chunking algorithm that just tries its best to group everything together that's in the same thing, right? Tries to capture these big squares and never like breaks in between two like squares or like different topics.
Yeah, there you have the added part that you can assume in most cases when it's human written that there is some inherent structure in the document.
Right.
And with the semantic chunker, if you do it like still basically in the flow of the document, you expect that there are basically blocks of topics, which are
yes, exactly, yeah, and yeah, exactly. I guess it's true. This is very much for doing like chunking long corpuses that someone's written, and it did a good job. It did a pretty good job. Yes, it's out of cluster semantic structure. I was really happy with that, and we used as well. I felt pretty smart. I used a dynamic programming algorithm to find the optimal chunking. That's pretty neat. It felt like a leak code hard challenge. Yeah, it was good. It was good.
What were the different parameters you were throwing in the optimization algorithm? So what were like the degrees of freedom in the end?
Yeah, you're completely right. Me and Anton originally agreed that we wanted as little hyperparameters as possible, right? Because no one cares about hyperparameters, no one wants to touch it, right? So the less there are, the better the algorithm will work because no one's going to tune it, right? And so I really tried, and this is a bit stupid looking back at that, I really tried to make something that had no hyperparameters. But if you think about it logically, there actually will always be, there has to be at least one parameter. And with this idea about trying to keep semantically similar chunks together, the optimum strategy is to just not every single sentence is its own chunk, right? Because obviously the most semantically similar thing is itself. So you do actually have to balance it a little bit. What I did, the way I did it, and I think someone could improve this algorithm. This is just how I did it, and it seemed to work quite well. But I first, obviously, the diagonals, I normalized the diagonal values. So down the diagonals was ones, because obviously the similarity between a document and itself is 1. I normalized that to instead just be the average similarity between all pairs, right? So that suddenly it makes the diagonal not that strong. And I made an algorithm that said, okay, like, basically, you're allowed to place. You could chunk. Because you can only chunk consecutive things. And this is another thing. I said it can only chunk consecutive things, right? You couldn't put one sentence at the start and a sentence at the very end of the document in the same chunk. That would make no sense. They're like completely opposite. They're not consecutive, right? So I said they can only chunk consecutive things. That means that effectively you're basically putting squares along the diagonal that always connect. Again, it's very easy. When you see the image of the matrix, it's quite easy to visualize this. It's basically you just have squares groups along the diagonal. And you're basically saying how big can I make these squares? How small can I make them along this diagonal? So that fixes another thing. And then you have how big can a chunk be? I said a chunk should be no bigger than 400 tokens. Sorry, yeah, 400 tokens, 400 words. And then I normalize the scores by basically minusing the average score to everything as well, actually. So that just normalizes the rewards function for a given chunk is to have the highest sum of similarity scores. Basically, that group appears as a square on the matrix, and it takes the sum of every matrix element inside of it. Of course, you'd say then the optimum strategy would make the square as big as possible. It would be if there were any negative matrix values, but there is negative matrix values because we subtract the average from everything. So if the similarity between two was slightly less than the average, it'd actually be negative, and it'd be worse to include it inside the chunking. That's a reward function. Again, somewhat technical to say out loud. I guess any algorithm explained verbally is quite confusing. You generally need some diagrams, right?
Yeah. Why did you choose the 400 words or 400 tokens as a cutoff? Why that value?
Yes, you're right. That is very abstract. It's not, because we messed around a lot. So I got a good understanding and intuitive understanding. Yeah, okay. Perhaps this is a good time to segue in to OpenAI's mistake. I believe OpenAI's mistake, right? It seems from my experience, we played around with a lot of different token and recursive splitters. And we found in general, around 400 to 200 token size chunks does really well for recall. It's actually really good for recall with both the fixed retriever and token splitter. And if you think about it logically, and I'm saying this because I study physics, and we always think about extremes. Like whenever you think about a problem, you always think in extremes, right? Like when it comes, let's say a fixed window splitter, right? The two extremes are like the window is like one character. It's the tiniest window as it could be. It's a single character. You would agree that its performance would be horrible, right? If it's just one character, split the document by single words, because there's no context there, it completely broke the document. The other extreme is that it's the entire corpus. You tune that parameter from 0 to a million or bajillion, right? And then that means it just grabs the entire document and throws it in. Again, really horrible retrieval. I guess recall is technically good, but very horrible performance overall because efficiency, blah, 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 is really bad, right? So clearly, there is like some sweet spot between 0 and a million. There is going to be some maximum. There is going to be some ideal width of a chunk. If you just think about it logically, if it's going to be bad on either side, it's going to have to be a maximum in between. And sure enough, we found around 200 to 400 things do really well. And my intuition for that is the reason why 200 to 400 token chunk sizes is good. And mind you, this is for OpenAI text embedding free large. Okay, this is all done with OpenAI text embedding free large. If you use a different embedding model, I don't know. Some people use sentence transformers. Personally, I'm not a fan. I think OpenAI's embedding models are great. But yeah, for OpenAI text embedding free large, which is also what OpenAI uses for their assistants, that's what their assistants use. We find 200 to 400 token windows are the best. And my intuition for that is that obviously if you make the window too small, you lose context, it won't get retrieved. The context will be lost, right? If you make the window too big, it dilutes the information. Suddenly you're covering too many topics. And if you're just trying to get a very niche topic that's within this massive chunk, maybe that it's some tax policy, and there's one tiny remark by tax policy that says, by the way, this has to be done by this date. But there's a million other things in the document, and you query, hey, when does this tax policy have to be done? Because it's such a small part of this huge document, it doesn't get retrieved. And in my opinion, that's like the sort of idea of dilution. So anyway, we find that 200 to 400 is around that sweet spot. And that takes us to OpenAI's, I think, mistake. They released recently the parameters of their new assistants. And man, my boss made a good point. They were so lost in their own hubris. They because they're embedding models, of course, OpenAI makes amazing embedding models, but they make some really their context windows are getting bigger and bigger. The embedding models of OpenAI, they have really big context windows. You can, if you want, you can stick 4,000 token documents into their context window. but it doesn't mean you should. And I think OpenAI got a bit taken away by it. I believe, I'll pull up the stuff, it's in the paper, that the OpenAI assistants use 800 token windows with 400 token overlap, right?
Yeah.
Yeah. It doesn't do so well. It doesn't do as good. Before they had 400 token windows and 200 overlap. And that did way better. And in my opinion, it makes sense. If you make your windows 800 wide, that's so much information. Obviously, your chunks should be slightly diluted. You can have a lot of different stuff happening. And if you're trying to get a niche thing back, maybe if you have really bland chunks that yap and yap on about a single topic, maybe. But otherwise, if there's a lot of stuff happening and you're sticking that all into this massive 800 token chunk, there's a good chance it's just going to be missed. It's just going to, the information, the retrieval for that single tiny bit is just going to be lost away. And it seems from our test that it does. And so that was like a blunder on OpenAI's part. Before, they used to have 400 token windows, and that was better. Like from our statistics, it shows that's better. They should change that.
Yeah.
But yeah.
Maybe an intuition basically on the chunk size why it could work. I think there are like general writing guidelines how long a paragraph should be, and it's mostly around like 100 to 250 words. And this basically comes down exactly to like this token range you also have if you assume like 2.5 tokens per word. This comes down exactly to it. And if you treat like a paragraph as a unit of thought, which is pretty coherent, you actually can come down to that.
Yeah, absolutely. Yeah, actually, that makes tons of sense. So yeah, you can see so much to this. And yeah, OpenAI blundered on that. But
why the large overlap? So can you maybe explain for what the overlap is in general? Like why do I actually integrate the overlap in the different chunks? And
yes, it's sure, of course. Yes, overlap. Now, of course, me and Anton, we in this project, and the idea, okay, what is overlap? Why do we have overlap, right? The reason why we have overlap is that these chunking algorithms, they can't see what's inside of them. Overlap only exists for these recursive tokens and the fixed token splitters. And the reason why, let's take the example of the fixed token splitter, it's quite easy to say, is that let's say you have a chunk size of 5 words, right? And you have a sentence. You can imagine that it's going to break that sentence. The chunk might end midway through a sentence. And the reason why we do chunk overlap is that if we break something by doing chunk overlap, the next chunk starts a little bit behind. And so that whole sentence, it would all have got broken in the previous chunk. And the next chunk, it covers it and it picks it up because it starts a bit before. So it's the idea that one chunk might end early, the next chunk starts early to catch whatever was broken in half. That's why chunk overlap exists. So fundamentally, it exists because the chunk have no idea what's inside of it. They can't tell. The chunk can't tell if it broke a word in half or if it broke a sentence in half. So we use chunk overlap as far as I'm concerned, as a way to basically deal with the fact that, oops, we may have just broke something in half. Let's start early in the next chunk. So it's actually, when you think about it, quite a hacky solution. And so with me and Anton in our project, we wanted the ideal chunker should have no chunk overlap at all, to an extent. There really shouldn't be any chunk overlap, right? I say to an extent because sometimes if you wanted all sorts of stuff, there was just one thing. You could have, let's say someone had a paper and they had multiple experiments. They had experiment A, experiment B, experiment C, experiment D. And let's say every paragraph they start with the experiment. They say, experiment A, we did so and blah, blah, blah. Next paragraph. Experiment B, we did so and blah, 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 and whatnot. One might ideally like a chunk which literally just says an experiment, like just the first sentence of each paragraph, all in one chunk. Because then if somebody asks, hey, what were the experiments done? You'd retrieve that chunk. Whereas another person might like a chunk of each paragraph. In that sense, there's been chunk overlap because you have information being repeated. But that's quite a complicated, tricky algorithm. And it's not quite clear how someone would develop such an algorithm. So we push that aside because that's like quite complicated. It's basically saying let's re-chunk for a different query. So that's like a different topic. And especially when your chunks are query independent, you have to you have to chunk overlap problem that ideally you'd rather not have. And ideally you would just have the chunks be aware of the semantics inside of them and split correctly so that they can just be left apart. So yeah, that's the whole thing on chunk overlap.
Yeah. One chunker I also want to double click on is the LLM-based one. Can you actually explain how it works and how it basically separates the text into separate chunks?
Yes. So we tried a few. My boss originally posed the idea, and I thought that was insane. I was like, this is silly. This isn't going to work. But then we thought about it, and like, okay, maybe it could work. And it was a fun experiment. Why not? The first one we tried was actually just silly. What we did originally was the original way is that we literally handed a massive chunk of the corpus. Like fundamentally, these models have a context window. You can't hand them that much information, right? So we hand the first 4,000 tokens. We say, hey, GPT, it'd be like GPT 4.0. Here's like the first 4,000 like tokens of a corpus. Can you respond to me like in quotes saying chunk one colon and then write a bunch of text and then chunk two and blah blah blah. And I tried that algorithm. Now, sure enough, as you can imagine, that had a million trillion problems, right? The very first problem being that it would just write its own stuff, right? It'd say chunk one and just go off on its own journey, right? Nothing related to the actual document. Or it would be similar. It would hallucinate. Before I worked in I worked in the edtech for a bit where I was quite used to having to parse outputs from GPT, like JSON parsing. And a thing I used to quite often do was like you'd validate its response. So I validated this. I would do an exact text search from whatever responded with the original to make sure that it's actually quoting the original when it writes out a chunk. And it would never quote it. If there was sometimes the grammar in the original chunk would be a bit dodgy and it would fix the grammar or it fix the typo, but then suddenly that's no longer an exact copy and all these things. That was a mess. And that didn't work. And more importantly as well, if you think about it logically, you're saying that the chunk of document, you have to pay the inference cost of every token in your corpus. That's really expensive, right? I think it's £15 per million tokens. Maybe it's not that. I don't know. It's not good. It's not good. Paying an inference cost for every single token in your document, like of GPT, isn't really a good idea. So we dropped that. And instead, we made a much nicer system, which was quite smart. Which was what I did is I stuck a bunch of tags inside the documents. And again, either seen then explained. You can see if you look at the PDF or the paper, you can see in the LLM semantic chunker what the text looks like after the tags have been added. So it literally starts with like open angle bracket, chunk 0, close angle bracket, and then there's some text, which might be some sentence, blah 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 blah, and then open angle bracket, end of the first like bit, and then the start of the next. And then because of this, I could then just actually ask GPT, I could say, hey, read through all these like groupings of the text and say what should stay together. So like maybe the first three groups should stay together and why. And they have to be consecutive. So in fact, actually, you just tell me when to split. So they might read like everything that's in the first grouping, everything that's in the second grouping, and the third grouping, and say it should split after 3. And so then we just do that together. And so by doing that, GPT can literally just respond with 3, 6, 7, 8. And then it also actually give an explanation. Like, I decided to split at 3 because blah, 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 blah. It turns out, I didn't see it because I was just passing it to Jason, but I had it print the output one time. It turns out it yaps a bunch more. But anyway, so it does that. And that's how it works. And honestly, quite surprisingly, it was pretty good. It actually performed quite well.
Yeah. So in the end, like the semantic one and the LLM one is basically you split up the text, you separate it into like chunks already, like into really small pieces, like atoms, and then you basically merge it back together based on, for one, the similarity, and in the other one based on whatever the LLM predicts.
Yes, 100%. Yeah. So similar ideas. Yeah, they're actually very similar ideas, yeah, in that sense.
Nice. What were the other chunking methods you would highlight from the paper?
So my Greg Kamrat, I'm really sorry if I mispronounced his surname, but Greg, really cool guy, cool with him. He's the guy who pretty much started this whole thing. He had that notebook that a lot of people saw, then like 5 levels of semantic chunking. He made a chunker himself, and his was cool. His worked by having like a rolling window, and we implemented that. Unfortunately, like, mind you, look, Greg made this very clear. He did this whole thing as a thought experiment. He didn't like rigorously try and fine tune everything. And his chunker performed very poorly on our metrics. But the reason why it performed poorly is that it produces really large chunks. Because it was never really, it produced chunks of over 1,300 tokens. And the bigger the chunks are, we've mentioned this before, the worse they would perform generally, right? If they're too big. And that's because, like, when he wrote this algorithm, he didn't realize that it matters a lot that you keep your chunks small. It's at least, in my opinion, it's a restriction of the embedding model, actually. That the chunks should be at a certain size, otherwise the retrieval gets a little bit bad. So yeah, so we tried a Greg's chunker, and it was alright. But it's a very important chunker. And we actually made an improvement to a chunker where we have a parameter into it that said, hey, chunks can't be any bigger than this amount. We said 400 tokens. And it actually improves it by quite a bit. That was another chunker. Pretty cool. And there was also another chunker, it was like a pinecone chunker. We tried that, and they were pretty good. I would have liked to include it in the paper, but there was stuff happening. And there was some other details that get sorted. Yeah.
And What were the chunkers that didn't make it into the paper? So the different mechanism you've tried and that blatantly failed.
Yeah, good question. Let me think. There are definitely a few. The semantic chunker. Mm-mm-mm. It's been a while, so we did chunker quite a while back. God, I'm really trying to think. Sorry, let me think. What chunker did we try that failed? Was it LLM semantic chunker? Yes, yes. Okay, sorry. Damn, I'm completely blinding. Context site. We did a lot. In the abstract, we have some of the failed chunking algorithms. And there was a paper called Context Site. Really cool paper. And what they try to do is, that whole paper was to do with citing, which is given a RAG pipeline, how can you cite? Yeah, there you go. That's actually okay. Yeah. So they had a paper where they're like, the whole idea of it was to like help cite where like your LLM's response comes from in the prompt. And I tried to write some nice algorithm that uses that. And that says, okay, that would basically like, it would basically like try and use the algorithm that they designed, a really nice algorithm, that paper. It would try and do that to find how relevant each chunk was to each other. That was one thing. It was somewhat of a messy implementation. Most importantly, the whole thing failed massively because it got really confused by Japanese. There was some Japanese text and it just seemed to throw off everything really badly because it all blew up. And honestly, I'm actually quite curious to know if it would. I honestly think that might have an effect on the normal paper. The context side people should give it a shot. It seems like languages go off the whole algorithm. Yeah. And then we also tried logic and attention-based chunking. And mind you, like, I'm not gonna lie, this was very much experimental, right? This is one of those things where you go in just being a little bit curious, but you don't really have a plan, and sure enough, nothing works, right? So I tried using an already good chunker, like kind of like a fixed token chunker or one of our cluster semantic chunkers, and chunking, and trying to see if we pass the entire corpus through Llama 3 and see what the attention models look like. I had the attention values and like the logits, and I'm trying to see, okay, is there any like signal here? Okay, for example, you can take the logits, right? At any given point, you can see the probability of a word being generated, right? By just running it through Llama. And so you might be like, okay, is there any signal in that? Do we see that actually suddenly the probability gets really low when it changes from one theme to another? And the answer is, yeah, a little bit, but not really. It's hidden in the noise. Think about it, the start of the next sentence, you could say anything, right? The probability of in the start of the next sentence is really high. Or maybe it's not that high and you start with the, but then after, you could say so many things. The tree, the cat, the man, the person, the block, the paper, whatever, right? And that was like all noise, and it just threw the whole thing off. Like you couldn't find the semantic changes within the noise. It's just how actually quite chaotic language is. But it's in our appendix if anyone's curious, and there's some cool pictures in there.
Yeah, I've tried something similar before. We basically tried to model the probability distribution of the logits,
Oh, really?
and it was chunky. I
Yeah.
had to do so many different assumptions and stuff like that, and it
Yeah.
didn't work so well. I think the logits aren't really optimized for like themes. They're
Yeah.
optimized for basically a single token output and
Yeah.
not for the modeling the entire sentence, for example,
Yeah.
based on which I basically have to chunk anyway.
Yeah, exactly. Yeah, that's it. Because as well, it very quickly jump back, right? If the moment the sensor starts getting onto something, immediately it'll just lock into something, right?
Yeah.
And so, yeah, you can never. It was hard to say. It never got confused. This idea that oh, actually, the tokens are like there'd be high entropy tokens where like it's given the probability to tons of different tokens. No, it doesn't. Like it very quickly locks into some theme. But yeah.
Yeah. If we would have infinite time resources at the end of this study, what chunking method would you have loved to have tried?
Hmm. I mean, I would have liked to think longer and harder about the very fundamental first thing we said, which is that the perfect chunking algorithm would take a query and find the relevant tokens amongst the document that answer that query. That's actually chunking algorithm. Like, it's all the chunking algorithms are great, but ultimately, that's actually what matters the most. Is you just want to retrieve the right stuff for the query. Yeah, I would have liked to work on that. There's something that, as I said, Colbert have some work on that. And there's something you could do with that. Maybe like some sort of sliding window technique where you like slide. That's not how it works anyway. But at the time, even just thinking about it now, it's just putting my head into a spin. There's a lot to think about because, as well, a lot of times it's disconnected. Again, the question is, can you get me the experiment names of every experiment in this paper? He has to retrieve a bunch of disconnected pieces versus can you tell me what give me the third sentence of the first paragraph? That's a very weird question, but someone could reasonably ask that. All these different things. But yeah, I think it'd be nice, and someone should. It's very important that one day, and this will happen eventually, that we have a chunker that can do that. It's not a chunker, like a whole RAG system that could really retrieve the exact tokens, because that's what fundamentally matters. That's something I would like to look into, but it's just hard to see how you can tackle that.
Yeah. And I think this goes more into the entire search literature or the traditional information retrieval literature again. They actually spend way more time actually thinking about what are the different query types you will encounter.
Yes.
And what are the documents I have, which documents fit to which document, to which query type. And then you basically try to deconstruct the entire search system and ensure that it matches in the most optimal way. And I think in RAG, we basically threw all of that away. We embed the documents, we embed the query, and we hope something good comes out of it.
Yeah, right. Yeah, no, exactly. You're right. It's true. It's a massive field, and people worked on for a long time, right? And yeah, I think it's true. We really should spend more time revisiting old literature.
Yeah. You already mentioned that you threw away one chunking algorithm or method you tried because of the language. Are there any additional language specific considerations for the chunker people should be aware of?
Let me think. Generally, here's what I'd say. I'd say with most chunking algorithms, and even with the ones we threw out, the issue was when we had a mix, where in the same corpus we had Japanese appearing amongst a bunch of English text. And the issue with that is that it seems like, and I know these embedding models, they try not to deal with this, but it seems like they still treat it a bit separately. They're like and fundamentally it's true. A Japanese word is very different from an English word. Even if the words are about the same topic, there's still one axis, language, where they're very different, right? I wouldn't say that the word, whatever, I don't know, the Japanese word for a tree is, and the English word for tree, yeah, they should be somewhat similar. They should be closer apart. They should be closer together than, I don't know, maybe tree and, I don't know, car. But at the same time, they're not the same. They are two different, they are words in different languages. So in the sense that in the language axis, if there is like a dimension in the embedding model, which is the language, they're very far apart, right? So anyway, so yes, you will find that there's going to be some disconnect in similarity if you have multiple languages in the same document. I think if they're all the same language, none of these problems should appear. If it's all the same language, then it's fine. That is eliminated. Yeah, I haven't. It's true. I haven't tested actually ask cluster semantic chunker amongst different languages. I think the LLM chunker would do just fine because it's a large language model and it's a smart machine. So
yeah, what was a thought experiment a while ago from mine was thinking about trying to bring or reduce the different words of Latin-based languages back to the Latin equivalent and training embedding model on the Latin equivalent. This is something I would love to try at some point.
That'd be awesome.
Because I think the embedding model gets more robust across the different Latin languages. Like if you take any of those, Spanish, English, German, all have heavy Latin influences. And if you basically trace back the origin of the words and embed that, this could be an interesting thing to try.
Yeah, that'd be really cool.
It wouldn't be worth the effort, but it would be like a fun research project.
Every one of those fun things, yeah. Those philanthropic things you do when you make you have tons of money.
Yeah. When you look ahead or during your research, did you find any research areas that you think are very promising or very interesting for the future of like document chunking or RAG systems?
I think we're happy with the cluster semantic chunker is good. The LLM chunker is good. They can be a little bit slow though. I think fundamentally, to be honest, I actually think that this is a pretty close subject, right? It's a chunking and it's the first part. I think we shed a good bunch of light on it. I think really though, what it highlights is that people should think about chunking, and ideally, I think I'm hoping someone out there can start thinking about the ideal token retriever, right? That's really the best thing. That would be a future line of research. We haven't actually made a dent in that because it's fundamentally very different. Given the query, can you retrieve the exact tokens in the document? How can you do that? I don't know. There's a lot you could do, but it's just very different from what everyone's been doing now. And like as well, the entire vector database kind of goes out the window when you do that, right? I'm not really sure. It depends how you implement it. I'm not sure, but it'd be very tricky. That's, I think, a very promising line of research. How you could tackle it, I'm not sure, but I think it fundamentally needs to be done, and it will eventually be done at some point.
Yeah. And if people want to basically get in touch with you, read the research papers, hire you, hire Chroma, where can they get in touch with you?
Yeah, it's true. You can get me on LinkedIn, Brandon Burr Smith, or go to my Twitter actually. What's my Twitter? It's Brandon Starksel. So that's Brandon Starxel. It's a bit random. That's just my code name on there. But yeah, you can get me on either of those, and come like my LinkedIn posts.
So what can we take away when we are building RAG applications? So current chunking methods assume text to be continuous, which is a correct assumption in most cases. Text flows naturally, ideas build on top of each other, sentences combine into ideas, and words link together to form meaning. But most chunking methods actually even break this flow. So for example, you have the sentence, the example Brandon gave. John buys a red Ferrari, it is the fastest in town. When you split by sentence, you completely lose the connection, and especially the second sentence loses a lot of context. What does it even refer to? And current solutions try to patch it by overlapping chunks. So basically, if we split by sentence, we might include the sentence prior and the sentence after and hope that the context is maintained. But this brings a lot of its own problems. First of all, we store the same text multiple times. We have to use more compute power. And also, it makes our database messy with duplicates. You might only retrieve chunks because of the included overlap and not because the chunk itself, without the overlap, would actually contain something meaningful and important for the user's query. And also, we have context that could be completely out of the flow. Of course, it can be in the chunk above, but it could also be in a different document, or it could actually be in the head of the person who has written the text. So overlap is really an imperfect solution for trying to contextualize the information. And we actually need better solutions to do this contextualization and also to do the chunking. And the solutions for that could be something like contextual retrieval. We could use LLM-based chunking, which is in the end a form of the contextual retrieval. Or as a quick and dirty solution, you can use the overlap, but you should be careful with that. If you implement it, make sure that the context is actually in a flow and is not coming from somewhere else. And one interesting thing, actually, which is my theory, why the chunk size works for 100 to 400 chunks or 400 tokens, it's in most writing guides, and this is followed by most writing, is that a paragraph is 100 to 250 words, and one paragraph handles one idea. And this really matches well with what the chunking research actually says, which chunk sizes work best, like 200 to 400 tokens. And I think this is actually the sweet spot, because if you treat a paragraph as a unit of thought, this really lines up that you take a chunk size which aligns with that unit, and it just makes it more likely that you have a semantically coherent and contextually relevant chunk. So when the chunks are too big, they dilute meaning. And when the chunk size gets too small, you basically break up the context too much that you lose the information. The two main solutions I think he came up with is, for one, the semantic chunking. And in semantic chunking, you split the text into small segments. I often like to do sentences, and then you create embeddings for each segment and measure how similar segments are to each other. And then you group related segments into coherent chunks. And you could do that unstructured, so basically independent of the order of these segments. What I like to do is actually use a rolling window. So usually I have a minimum chunk size and a maximum chunk size, and I slide over the document and measure the similarity. And once the similarity to the next sentence basically is below a certain threshold, I basically say, okay, we have to create a new chunk. And I basically build on the assumption that the authors spend some thought in the order of the document and that it's not like completely independent. And through that, I basically try to find natural topic boundaries in text to see like when one topic ends and another begins. I basically create two different chunks and I can avoid a little bit of the overlap issue. The second solution he found was the LLM-based chunking. So you basically teach the machine to think a little bit like an editor. And you use a language model to read the text and decide where it naturally breaks into parts. So the LLM marks potential breakpoints with a special token. And then you ask the LLM to evaluate these points. And then you have basically a decision which sections should stay together and which should be split. And you use these decisions to create the final chunks. And this really banks on the idea that LLMs actually can understand context and meaning. And I think this method really has evolved into the contextual retrieval by Anthropic, where you, on top of basically the chunking, you add back in the contextual information. So you basically have the entire document, you look at the chunk, feed it into the LLM and ask it, hey, what's missing here from the context of the document that I should insert? And when I use it, I don't just feed in the prior document, but also important definitions for the field, which might diverge from like the knowledge base of the LLM. So usually you have different definitions of something depending who you're asking or who you're talking to or what field we're in. And you usually also include these definitions to basically make it contextually relevant. If we had a legal use case recently where we also included a lot of like legal information, basically like different paragraphs and stuff like that, to also contextualize it even more. And through that, you basically try to create like semantically different chunks, but still try to get chunks that are completely self-contained and contain all the information you might need to answer questions about that chunk. And I think this is a really interesting approach. I think we are evolving into a future where the size of the information isn't the driving factor, but for that we also need better embedding models that can handle longer chunks. And I think we have seen one come out recently, which is Modern Bird, which performs better on longer context windows. And if we get there, we actually can be more flexible in the chunk length. So we can actually create chunks of different sizes or with different size context windows and focus more that they are semantically self-contained and handle only one topic. So to recuperate a little bit, best practices for now is like keeping the chunk size in the sweet spot of 200 to 400 tokens. This is something we already heard by Niels Reimers in our podcasts. I will link to it in the show notes. And also figure out a way to keep the chunk semantically coherent and self-contained. If you want to hear more about that, I have had a recent episode with Max Buckley where we really went deep into that on how we can do it. So yeah, that's it for the episode. If you liked it, let me know below. Leave a review. It helps us out a lot. Otherwise, we will continue next week. I wish you a happy new year. Otherwise, I will catch you soon. See you.